Good day to you. This is Galactic back with you with our second presentation of the evening in this new series on geometry. It's entitled Rational Geometry. These words are selected to demonstrate an approach toward geometry, obviously, that has something to do with rationality. What's that? It's a mathematical term, but it's also a logical term. To be rational is to be logical in a broad sense. But in mathematics, it actually has a specific meaning. It refers to what does it refer to? How do we use the word rational? Well, I'm casting about in my mind for the easiest way to make this simple, because it is. And for some reason, it's not treated as a simple thing. But a rational number is one that is not irrational. And so the key to understanding what is a rational number is what is an irrational number. And then we'll be able to come back and talk more about what is a rational number. This is extremely important, and it has to form the basis of any approach to geometry. I rarely, if ever, have seen geometry presented the way I'm intending to present it to you now, because this, what amounts to a new approach to explaining what it is, has a specific purpose, and I'm approaching the topic the way I am, which you haven't heard yet, but you're about to, in order to underscore, this may sound pretentious, but it's to underscore the most important aspects, which I have basically discovered have gone really unnoticed. These are critical facts, factors, basis definitions. What is a rational number? You could answer that directly, and that's why I was casting about there for a moment, but it occurred to me that the easiest way to define a rational number is first to define, what do we mean by an irrational number? I believe that has an easier definition, just to state it out loud. What is that? It's a non-repeating infinite decimal number. It's a number that literally cannot be computed. It's a number that cannot be represented. It's a number that, in a sense, is not a number. And believe it or not, although that may sound like the most harebrained or nitpicky thing, this has been hotly debated for centuries. And so it really seems, just from that fact, you can assure yourself of that by looking into the subject. What men have said about irrational numbers, that what makes them irrational, it's known what it is. It really is that infinitely repeating, not infinitely repeating, but an infinite number. It has an infinite number of pieces. Each one of those, when we say infinite, we're in the decimal numbers system, but it actually could be any number system, binary. They all do the same thing. And why is that consistent? I wanted to mention this, and now's a good time to do so. Excuse me for divagating just a little bit, but each one of these pieces is absolutely critical, and I have a whole palette of them to present to you. To put it together, this is synthetic geometry. It's quite difficult to do. It's difficult to present, because what you're presenting when you have a synthetic approach is an overall strategy that was overlooked because if you're getting the solution that was unknown either to you or perhaps to anybody, and you and you used a synthetic approach. Well, when do you do that? When do you use a synthetic approach? When you're not doing analysis, when you're not breaking things down to get a computed result. A computed result is the result of analysis. But with synthesis, you don't get a computed result, you get a structure. The structure is something that it's a goal, just like a computed result, which would be numeric, obviously. But the other side of that, and they go together, they're inseparable. You do analysis to get your numeric result, and from your numeric results, you get knowledge. From data, you get knowledge. That is the goal. But then what do you do with the knowledge? Well, you actually have to put it back together again. You got your information that you wanted from the universe, whatever part of it you were measuring. You have your numbers, so you have your results, including your propositional statements, which have either been validated or not. So now you have more than just numeric results. You have statements in English or whatever language that you know now are true. Well, that's really what you want, of course. And by the way, every equation, which is synonymous with formula, a formula and an equation, that means exactly the same thing. But that is a statement. It's an English statement if you speak English. And it makes sense. And how many times do you see that written below the equation? Never. You never see any, but you know why? Well, you might want to guess why, but whatever the reason is, it's not good. Every equation should have the statement that it makes right below it. Every time. Because you can't read that. It's shorthand. The reason we use those symbols in the shorthand is it makes it so much easier to line up. But once you're done, you don't have to do it for every single equation if you're doing a series like in a proof. But you do it for one of them. They never do. You never see that equation. I'm talking about translation, just translate it. Of course, they're trying to explain what they're doing in the next paragraph, etc. But when you see it's on a printed page or it's on a blackboard, well, you have to say what it says. It's written in a fucking foreign language. Well, part of the reason that that's done, at least in classrooms, is to train you to get used to that. Well, that's fine if that's what you want to do, but that's really not mathematics. I mean, not mathematics. That's really not. It's really not correct presentation. You're presenting code. Well, this is the very reason why in programming, programmers are notoriously lazy in annotating their work. Well, it's just, they're killing everybody when they do that themselves. They're shooting themselves in the foot. There is a school of thought that you should have a comment after every line of code. Well, I think that's overdoing it, but you do need to have regular ones. I prefer to have it before every logical block of code. I myself skip it if I'm in a hurry. We're all in a hurry. That's always the problem. But that's really inexcusable, is to leave out what the thing actually says. If you're writing in code, the person reading it is not going to be able to read it in code. Although, I mean, it's almost like it's a game to see who can read this shit the most. Well, that's just wrong. You don't have your ability to understand something should not depend on your ability to read code. It should be on your ability to reason. And for that, you need sentences, not code. They do say the same thing, but you see my point. It's the same thing as with annotating your programming code. Why would you leave out the translation? It's going to help you to do it, to translate it for yourself. It's one reason I make these videos, by the way. I look at these videos and I study, I listen to myself. I'm not kidding you. Every now and then I learn something. I was talking, because this is new, I discovered a new geometry, so that's where we're at. So in approaching this strange claim that I've discovered a new geometry, I find it should be simple, right? If it's geometry, yes. So how simple is geometry? Well, we figured out, you and I, in the last lecture, and this is the continuation of the previous lecture, but I will endeavor to sum it all up right now, as I should. We did find out that there is an object associated with a number system. This is simply, it's been proved. But what's strange is we've only used one object, and therefore we only have one number system. But the statement is true, that our number system and the object that it represents, are the same thing. They're not the same thing, or they, well, obviously they're not the same thing. Well, what are they called? The line is an object. But the number system is actually the numeric representation of the line based on the metric of the line. And the metric of the line is what defines the relationship between the numbers in the space. Now, on the line, that is so simple that we take it for granted, but let's state it obviously, because in a new geometry, you're going to be doing the same thing in a new space, which is what I discovered, so get ready for this. This is how to get ready. We just look at the line, and then we're just going to repeat everything for the line for the new space and make sure we don't miss anything and see if we can do it. So what are the things we need? We're going to need a new object other than the line. Well, there's actually only one that can be used to, and if you find another one, be sure to let everybody know, because so far nobody's found any other object except the line. That's true. That can be used to formulate space. That's why we use the line, is because by making 3 of them, that does fill the space, but it fills it with cubes, and that no longer works in outer space. You can't fill the universe with cubes. You can do whatever you want with the cubes on Earth and then shave off the edges and make a sphere. But to do that, you use calculus, but you have a remainder and you throw it out in what's called the delta. On the derivation of linear numbers from curved space, you lose something. And so we cannot compute the sphere. Well, this is the reason why we can't compute the sphere. Or the circle. The circle is represented by tau, and believe it or not, the sphere is represented by 2 tau. What do those numbers mean? Tau is the most irrational number that a human being could imagine. It's the number that represents the relationship between the line and curvature. Actually, the circle. The relationship between the line, geometrically, and the circle, which is also a line, but it's a closed curved line. This is a straight line, because it goes to 2 infinities, because it's subtending a sphere, is why there are 2 infinities, because when it gets to the outside, it touches the sphere at infinity, but that's a sphere. That's why linear space is already embedded in spherical space. Can that be integrated? Yes, and that's what we're going to do, but let's see what it is that we're going to do so we understand what we're doing as we do it, and then you'll be able to do exactly what I did to make this incredible discovery. But you will have to do all the steps I did, and I'm giving them to you now. It begins by recognizing what the line is. It is an object. It is a number system. It has a number of components in its number system. In the case of the line, it's always one component. Because a complex number has two components. Don't forget that. We're not dealing with complex numbers, but I said that to let you know what's the difference. A two-component number literally has two linear numbers in it. Well, in complex numbers, that's not the case, but it does have there's two linear coefficients for two axis bases, of which one is imaginary. But in this case, we're just talking about the component numbers, nothing to do with I or any, just numbers. Well, that would be a two-component number. So in order to have a geometry, you need an object that has a number system, and it has, what did we just say? It has a metric on the object that defines the number system. That's the right way to say that. The metric is very interesting and depends entirely on the space. You simply search the space for the metric. This is how we discovered how to use the line, and indeed why we call it the number line. Because if you draw a line, you can first start out by imagining that it has an equal number of spacings. And if it does, you have a linear number system, but what does it mean? It means distance. It means distance, but then it doesn't have to mean distance. That is how we think of it, but it's actually linear magnitude. It's how far the number is from something. Well, in the case of 1, the first counting number in linear space, it's a distance from something. That's not exactly how the number 1 was first used, because nobody had ever even imagined that there was a 0. That's a true story, and it's really worth studying if you're interested in that kind of thing. Of course, a scientist is always interested in that kind of thing, but it really depends on your interest level. Everything's worth knowing, but who has the time? That's the only limitation, is time. It's definite, but that is a very interesting story, is the discovery of the number 0. And then it took a while. We knew about negative numbers, but they were resisted. The 0 was highly resisted. And then they were useful, so they stayed. But finally, it was realized that that is a complete system. That when you have 1, 2, 3, 4, you have a line segment. When you have 0, 1, 2, 3, 4, you have a line ray. But if you have 0 and then +1, -1, +2, -2, and it goes off like that, that's a line. The density of the line, because you know there's numbers in between 1 and 2. There's numbers in between 0 and 1. How many? What are they? What are they called? What do we do with them? Very interesting question, which has engaged the minds of the brightest men on earth for centuries. The nature of numbers. But it was finally cracked in my lifetime, and the answer to all those questions is very simple. All the numbers live on the line. There are no numbers that are not on the line, and when you draw a line, that is all the numbers. That is one of the most remarkable discoveries I've ever heard. The identity of an object with a number system immediately raises another question, because it sounds like we may have a scientific solution. Can't even call it that. It's much, much stronger than a scientific solution. We have the opportunity now to discover, devise, come up with a solution for science itself. That doesn't happen very often. So the goal now that we know that every number system has an object, and every object has a number system, what is strange is there's only one of each of those that we know of. There's only one of these pair, the straight line and the number system. They are so closely related, even before the proof, that we do think of them as the same thing. I know that that's true, but it's very interesting to see it explicitly stated. They are the same thing. But you're not done. In fact, you're just beginning. This is a gold mine because now that you know that, you know that this is actually a thing. But it's more than any. We always treated the number system and the line different because the line is for geometry and the number system is for computation, for mathematics. But to find out that they're the same thing, well, that is fantastic. But it does raise a very interesting potential. Could there possibly be another object similar to the line that has a number system? If so, you're going to need to find some other things because the line has more than what I just said. That zero has a very specific definition. It's called the Archimedean balance point of the space. Accept that. So whatever other object we choose will have to have another Archimedean balance point. Because it's a different number system and a different object. If it had the same of the line on anything, then it doesn't. Everything has to be different, right? That should make intuitive sense. That's not necessarily true. There might be certain characteristics shared. In other words, we might find another number system for the line. Is that possible? No. It only has one, because there's only one Archimedean balance point. Also, there's only one operator. Now we have a list of characteristics of the line. By the way, what is that operator? It's add. And that's the only operator on linear space, is add. We imagine that there's another operator called subtract, but that is true. But it's easier just to say add and remember that it's both, because all you're talking about is reflection around zero. There's no difference between the negative numbers and the positive numbers. And don't be fooled by the square root of -1. That doesn't prove anything because the square root function is an illegitimate function. The square root function is it's treated as an operator, but it's not. It's a foolish thing to do that has to do with the problem with division in linear space. And that really is a problem, and here's why. If you accept that the line has add and then obviously subtract, it can be proved and has been proved that that's closed on the line. In other words, any two numbers that you add that are on the line will result in another number on the line. That is also true for subtract. There's no way you can fall off the end of the line because there's always more numbers, the definition of infinity. Well, it's retroactive definition of infinity insofar as your definition of infinity affects the numbers in the space. Very important to say this accurately because we're going to get the right definition of infinity as part of the deal here. So in linear space, you start with a line, that's an object, you get a number system, you get an Archimedean balance point, and you get an operator. For linear space, that is the line, the linear index, the linear indexing system to get the computable numbers, that's simply 1. And then you have -1. Then you have 2, you have -2. And that's called the index, is how you define from the Archimedean balance point to the first counting number. What is that? For us, it's distance. Because on a line, That's practically the definition of distance. And this is why. It's because you can metricize it, 1, 2, 3, 4. On the Archimedean balance point, using the single operator, add. And then you're done. That's the end. Now you're done. But you have those 4 components. Now, what if there were another object? I asked in a previous lecture, as kind of a quick exercise, just test yourself. What other objects might there be besides the line? Well, you might think of the circle. That's a very good one. What about the triangle? About the square, the cube, tetrahedron? Any of the Platonic solids, some other hyperbola, parabola, an ellipse? Do any or all of these have a number system? Not the triangle, because it's composed of 3 lines. And therefore none of the polyhedra, in fact, none of the polytopes, which would include polyhedra and polygons and polyhedra, 2 and 3D. Straight line figures. Those would not be a new number system. But what about the circle? Well, actually, we found something very interesting about the circle in that sense. Complex numbers are closely related to the geometry of the circle. But why? Partially because it's a 2-component number. And a 2-component number gives you an extra degree of freedom to go off the line. Right? Now, if you go off the line consistently, it comes back as a circle. But that's saying something. That's 2 orthogonal forces at right angles that are basically balanced. So you have a motion going this way, or a force, something that's linearizing, something that's on the line. It's proceeding, it's going on. It's increasing in magnitude. From 0 toward infinity is the general direction. But you also have an orthogonal one going in this direction. What if they go at the same time? It would go, instead of going straight up or straight this way, it would go partially up and partially that way. And if they're both consistent in time, that is, they're synchronized, so that it's the same rate, then this will go like this. Now, what makes it go in a circle, though? Because if these increase like this, it goes in a straight line diagonal. So what are the 2 components that make this go in a circle? It is these 2 forces, but balanced on the natural logarithm. And that's why e to the theta I power, or excuse me, e to the, how does that work? It's e to the I pi. Is that right? E to the pi I. Is that right? Yeah. Yeah, that's it. E to the pi I equals -1. The reason that's true is e is a relator. It is called the natural logarithm, which is extraordinarily difficult concept to grasp at first, I think, is why e is such a special number. If you accept that it's magical, it's another story to find out why it's magical. That's actually even more difficult. But just to see why why any number would do what it's doing, e, if you use it right, creates a circular function. But all e actually does is balance things. It is often stated, and accurately enough so, that e is its own derivative. That's a profound statement, but it would take us far afield to discuss why e is its own derivative and how that could possibly, that gobbledygook could possibly even mean anything. It does. But the long and short of it is, you have a constant rate of change manifested as a circle. And those can be equated together to produce an equation of the circle. It's the relationship between x and y in some way. Well, how do we actually do that? Do you know? There's several ways to do it. It's called a parameterization of the circle. And what we're going to be getting into probably next month, I'll be ready to start telling you about we're going to have to learn the value of a certain discovery that's come up in my lifetime. It's called rational trigonometry. And rational trigonometry is for real. It's getting some attention, and I'm a tremendous follower of its discoverer. His name is Norman Wildberger. He's still doing well. He's retired from teaching in Australia, but he's attempted to revive rational trigonometry. And his series on rational trigonometry it's so extraordinary and so important and so amazing that literally nobody can understand it because they're too stupid. The physicists don't know what he's saying. Nobody trusts him who's into industrial pseudoscience. They can't understand what he's saying because he makes too much sense. There's too much truth in what he says. There's too much that shakes their foundation because it challenges them. They're cheating with their mathematics, and he's pointing it out. Well, I'm not only going to point it out, I'm going to correct it because I know exactly what these cheaters are doing wrong. You don't want to blame them, but you do have to characterize the demographic. It's not slapping anybody in the face and you're a dirty cheater. But if the shoe fits, you fucking wear it. Yeah, this is deadly serious. Calculus is it's miraculous and it's a cheat. It's miraculous on Earth, and it's quite interesting to prove why it only works on Earth. But since this has been the subject of debate literally for centuries, you and I are probably not going to be able to resolve it. I am, though. I will definitely resolve it. And you will be able to, too, when I'm done with you, because this is high time this all got solved. Well, the answer to the whole thing is you're using the wrong number system for curvature. Straight lines. And so here's the answer to the quiz. We've come up past 30 minutes, so I'm going to wrap this up. For the linear number system that we use in worship and admire and cherish, and we can't lose it, and we won't, believe me, but also prove that we won't lose it, you have 4 components. An object, the line. A number system, which it's the one that you and I understand. It's worth defining the metric because it'll come up again with the next object. So let's say it that way. It's the line is the object. Arithmetic is the metric, which is defined as the jump from 0 to 1, is the first counting number. In fact, let's say that. You have an object, the line. You have a counting number. That's 1. You have the Archimedean balance point. That's 0. And you have an operator. That's add. Now, there's footnotes to each one of those, but we're just get it out of the way. Now, is there any other object? There is the circle, but there's a problem with the circle in choosing that. It's already, it's linearized. In other words, the choice when you go from the line to the circle is to ignore the third dimension and just go into the second dimension and stay there. That's why these are called plane figures. They don't involve volume space. We would like to attempt to get volume space directly, because the reason the line is inadequate for volume space that it makes is that it doesn't match what we actually find in physics, which, simply speaking, is that the universe is not linear, but the universe is spherical. So what's the other object? The sphere. Okay, now let's get the forecast. That's the first one. The object is the sphere. We're just giving it a shot. Let's try it out. Before it was the line, now it's the sphere. The first counting number. Well, let's get the Archimedean balance point first, because you have to measure from that to get your first counting number. The Archimedean balance point of the line is 0, and therefore the first counting number is 1, correct? So far, so good. And the operator is add, because 0 plus 1 equals 1, correct? And therefore 1 plus 1 will be the next counting number, and you can call it whatever you want. Then you can choose binary or decimal or anything you want, but the units will be the same. And that makes a perfect geometry, and your metric is based on your first counting number and the definition thereof. It's distance in this case. Right? All makes sense. Let's fill in the blanks now. We have the sphere. What's the Archimedean balance point of the sphere? We haven't said yet. What's the first counting number on the sphere? We haven't said yet. And what's the operator on the sphere? Well, now here we could make a good guess, because there's only one other operator besides add, with the additive inverse of sub. So what's the only other operator? It's mult. It's multiply, with its inverse division, which, by the way, division does not work on the line, and that's why it's multiplication and division are not 1D operators. Only add and sub are. Well, now we have another clue. Maybe mult is the operator on the sphere. Let's assume it is. Let's assume that the sphere has an operator called mult. Now, what would that mean? Well, first we have to examine the space. What's the shape of the space? For the line, it's a line. What can you do with a line? You can put a midpoint on it, right? That's what you do, and that's 0. It'll end up being 0. But you don't say it's 0, you just make a midpoint. That's called the Archimedean balance point of the space, because you're balancing two infinities. They're equivalent infinities in every sense, for the reason that it's subtending a sphere. It's the diameter of the sphere. We'll get to the fact that the universe is a sphere. All of this fits. It's just incredible how all of this fits together and explains stuff that we've never been able to explain. But we don't want to get off on a tangent. We want to get to the point, because we're coming up on 40 minutes, and then we're going to end it. And then I'll give you another lecture. This gets better and better and better, but isn't it good already? We have a sphere. Multiply is the operator. Okay. What would be the Archimedean balance point of multiplicative space? Well, we know what the Archimedean balance point of linear space is. It's 0. And you know what we say about that? We say that it is the additive identity. The additive identity is 0. Well, then all we need to do is find out what is the multiplicative identity. That is well known. It is the number 1. Not 0. It's 1. So that's different. The object is different. It's not a line, it's a sphere. The operator is not the same. It's not add, it's multiply. And the Archimedean balance point is not 0. It's 1. And so what do we have left? There's one more characteristic, correct? What was it? We have an object, the line, or the sphere. We have an Archimedean balance point, 0 for the line and 1 for the sphere, and we have an operator, add for the line and multiply for the sphere. Now we need a counting number. What's that going to be? Well, what's the first counting number for the line? That's 1. What's the first counting number for the sphere? You might guess 2. You would be right, except for one interesting thing that we haven't talked about yet. The sphere is not at all shaped like the line. It's going to need more than one number to even say what it is. That is, anything in spherical space is going to require more than one number to identify it in spherical space. Because if you could identify something in spherical space with one number the way we do with linear numbers, then it would be the line. But these are numbers that don't come from the line. They come from the spherical space. See, the line is the linear space. That's why all the numbers are the same. They have, well, obviously they have to be the same in some sense. They're the same linear distance apart, but it has to be linear. If that line curves, they're not the same distance apart, you see? That's right. As soon as that line starts to curve, these are not the same distance apart as you go. It will change. Now, they could be said to be the same distance apart if you turn it into a circle, but the metric has changed. They're certainly not the same unit of distance apart. In other words, the 1 is not the same 1, because if you twist the line, it contracts the space. It's weird. But we don't want to get off on any tangents. The harsh fact is that we would need a 2-component number. Now, it's possible you might say a 3-component number, because that's how we compose 3D linear spaces, with a 3-component number, x, y, and z, or x, y, and z. But that's because you're using 3 lines, so that doesn't even count. You're using lines when you do that. We don't want that. These won't be These will be component numbers that have a relationship between them. In any other object, you're going to need 2 numbers. Because if you only needed 1 number to express something in the space, that's the definition of a line. We're going to surmise, what if that sphere can be fully parameterized? It's not the sphere, but the space. Can the space be filled with numbers? If it's a line, yes, you can fill the line with numbers. Can you fill the spherical space with numbers? In order to do that, you'd have to have some idea what that spherical space is. Well, it's at least 2 things where the line was just 1. The space of the line is inside the line, but the sphere has an inside and an outside, doesn't it? We're going to surmise that on the inside is one of the component numbers, and on the outside is the other component number. And together, based on the relationship between these 2 numbers, this would be for any 2 numbers. Based on the definition between them, the relationship between them, those numbers will live in spherical space. That doesn't seem to make sense, I must admit. But if you stop and you really think hard about why numbers are on the line, it gets to be really philosophical. And there's no real reason to just poo-poo, well, there can't be any other numbers. Yes, there could. There could be a number system for the sphere based on 2-component numbers. It certainly seems far-fetched, but we've already found a pretty close match that the sphere is a strong candidate for a number system. It has an Archimedean balance point that's, instead of 0, it's 1. It has an operator that instead of add, it's multiply. The object is not a line, it's a sphere. And we're adding to that in any space, you need to specify the number of component numbers, that will be unique to the space. Well, for the line, it's just one number. And we're going to say that for the sphere, you need two numbers with a relationship. That relationship is multiply. And so the relationship between the two numbers is going to be multiplication. But how in the world does that make sense? And where does the sphere, how does that even have anything to do with the sphere? Think of the sphere as the number 1. This will be true, so you're not harming yourself by thinking so. Think of that, and that is the Archimedean balance point then. Then the sphere is the Archimedean balance point of multiplicative space. That's correct. So we're just saying that. We haven't proved it. We're saying the sphere is the number 1 in the new, but it's only one. Shouldn't it be two numbers if I just said so? Yeah, it should be. Well, let's say it's 1 times 1. Good. So now you have the definition of the sphere. It's 1 times 1. So where do the other numbers live? Well, you still can't say. By the way, if you're putting the numbers in the space, we just finished the job. Because now all the numbers are in the space. The space is the sphere, and there's only one number. Not a very useful number system. See, the line has an infinite number of numbers on it. But I just said the sphere only has one number on it, and I'm just saying it's a two-component number, 1 times 1. That's useless. I haven't said anything. Now it gets magical. The way nature actually uses multiply, we already know. Do you know how I know that? Think of what is velocity? Isn't it distance over time? Yeah. Well, isn't that multiplication? Yeah. Yes, it is. Distance over time is a multiplicative operation. Distance over time is a multiplicative operation. We call it division. It's the same thing as multiply inverted, correct? Of course it is. So we already use a two-component number. Velocity is a two-component number. It's distance in relationship to time, right? That's a multiplication. But you have to flip one of them, right? Because it's not multiply, it's divide. Well, the definition of that, if it's m times n, right? That's not distance over time, that's distance times time. But it's not, it's distance over time, right? So what is distance then in the relationship? It's called the whole number. And what's the one on the bottom? That's called the divisor of the number. So if 6 is on top, that's the whole number. And the number on the bottom is divided into it. Right? Correct. So the top is the whole number, and the bottom is the divisor. Nothing demonstrates that more clearly than 5 over 1. Any number over 1. What does that mean? It means a whole number 5 divided by 1. That's 5. But what about 4 over 2? What's that? That's 2, but why? Because 2 goes into 4 2 times, correct? All right. Then rewrite 4 over 2 as multiplication. Do you know how to do that? You take the number that's on the bottom, right? And you flip it to 1/2. And now you have the multiplier. Instead of the divisor being 2, the multiplier is 1/2. That's saying exactly the same thing. And that's a unique property of multiplicative space. That's why 1 is the multiplicative identity. Because if you put 1 over any number, you are able to rewrite division as 4 over 2. You rewrite that as 4 times 1/2. And they mean exactly the same thing. Now, let's say that the relationship between the numbers on the inside of the sphere and the numbers on the outside of the sphere are that relationship. That's called reciprocal relationship. So that, for instance, on the inside is 1/2, and on the outside was 2, then the relationship between those two numbers would be reciprocal because they multiply to 1, correct? Well, that makes 2 and 1/2 reciprocal numbers. And therefore you can put them together to make a number 2, 1/2. And that's your number. It's like a complex number, except it's defined differently. But they're both 2-component numbers with a relationship. By the way, the relationship between the 2-component numbers in a complex number is add. You add them together. 2 plus 3i is a complex number, and the relationship between them is add. You add them. That's why they're complex. That's weird. But in the case of this 2-component number, they don't add. They multiply. See the consistency there, although I used complex numbers as an example. We'll come back to that. This all fits together, but this is very simple. Yes, of course it is. So that's the simple answer. Although we're not done yet, obviously. But now you could say, for just this one number, 2, if it's on the outside of the sphere, then you could say that the other component of the 2, which is outside the sphere, is 1/2, which is always inside the sphere. Well, that defines where the fractions live in multiplicative space. The fractions live inside the sphere. Now, all fractions, these are specific kinds of fractions. They all have 1. It's 1 over 2. In other words, the numerator is always 1. That's the reciprocal of a whole number is that number under 1. If the number is 6, then the reciprocal is 1 over 6, not any other number but 1. So if you have 2 over 1 on the outside, and you're looking for its component number, then you know what and where that number is. It's paired number in reciprocal space, which is multiplicative. It's paired, the number paired with 2 on the outside of the sphere is 1/2 on the inside of the sphere. And now you see something magical happen. That's all the numbers that are needed to fill space. It doesn't do anything. I'm just pointing out that it works. That in this number system, we've been completely consistent. That we're saying the sphere is the object instead of the line. Its Archimedean balance point is 1 instead of 0. And that the sphere itself is 1. So far, so good. You can say all these things. Maybe it means something, maybe it doesn't. But does it then fit? Well, if you go on to say that the space is defined by 2-component numbers that are reciprocal, then you actually can make that work. Because now all the whole numbers are going out from the sphere. The 2 is not inside, it's outside. And the fractions, which are all less than 1 and greater than 0, all fractions are less than 1 and greater than 0 in this space. The only peculiar number, and this corresponds to the 0 in linear space, the only peculiar number in this space is the sphere, which is 1. Correct? Hold that thought. We're coming up on an hour, and I don't want to hit an hour. It's 55 minutes. So this actually is going to work, but I'm showing you how I built it. These are more or less the steps that I took. Struggling with this for months. But when it all snaps together, it's the most amazing thing I have ever seen in all of mathematics. It's well beyond that. It's mind-boggling. A new number system. And I'll show you, even with the rudimentary knowledge I've developed of it already, that's quite consistent and so far has no flaws in it. This, by the way, has no holes in it. There are no singularities in spherical space. That has far-reaching implications already on the black hole and on the Big Bang. And the construction of this space on spherical shells, as you're starting to see it, that number 2 would be perhaps a spherical shell. It is. And this absolutely defines quantum mechanics, geometrically. Unbelievably so. I'm an expert on the paradoxes of quantum mechanics. Expert on them. This geometry solves all of them. It also solves the problems of astrophysics, like knocking over a series of dominoes. And I'm showing you the rudiments of the mechanics of the new number system, which is so remarkably easier than the system we use. It has no need of calculus. It's a very different goal, though. It's quite amazing. And so infringes directly on the human equation, because now the goal is no longer industry or money or the earth or survival. The goal is understanding, and since this is now absolute, this is the path of wisdom itself. It's the logical side of it, because wisdom obviously applies across the board to a much greater span and scope of life than simple science. But for a rational man, for a logician, this is the way to heaven. And that's stay tuned. You don't want to miss these lectures. I'm getting old. No one else is going to ever tell you this. We'll be right back.